Okay, let's get started. Welcome everyone, welcome to week 2 of CS50DC. This is lecture 1 of week 2. We're also going to do a lecture tomorrow as well, so if you could try and attend that, that would be great. So, let's just have a little think about what we've been doing over these last couple of weeks. First of all, what we did is we started looking at computational thinking and what it means to go down the lines of computational thinking. We then quickly moved on to implementing ideas of computational thinking using a graphical language called Scratch, where we explored ideas like events and functions and variables and arrays. And you've been exploring those further in the workshops, implementing your own Scratch projects for PSET 0. And what we're going to do today is we're going to take those concepts that we looked at, the ideas of functions, variables, arrays and more, and we're going to see how we can implement those in a much lower level language called C. And so for the first 10 to 15 minutes of today's lecture, I'm going to be comparing what you've done in Scratch to how that might be done in C. And when I show you the C programming language, you might be a bit overwhelmed. You'll be looking at things like, well, there's semicolons there, and there's parentheses there, and there's quotation marks, and there's hashtags, and there's these words that I'm not quite sure what they mean. But once we overlook those, and we focus in on, remember what we're doing, we're just trying to solve computational problems. And just as we could use this blocky interface in Scratch that was quite intuitive for most of you, those ideas, they're the same in C. We just have to implement them slightly differently because we're going to be using a textual-based language and not the drag and drop interface that you've been using in Scratch. So you remember that in Scratch we use something like this, which we call a block, and we've got here, when green flag clicked, say hello world. So when the green flag is clicked, when the program starts, what we're telling the program to do is implement or execute a function. And that function just so happens to be called say. And with that function we can pass parameters, or we actually pass arguments as parameters to that function. And I could have typed anything in here, and when the green flag is clicked, Scratch will appear with a little comment box floating above his head saying hello world. And this is how you'd implement that in the programming language C. And again, remember what I said, look past all of this syntax, look past this what may look quite cryptic \n, quotation marks, we've got hashtags, again we've got parentheses, we've got curly brackets, and just realize that in C, this would do exactly the same thing as this. We've got this thing up here called int main void, which we'll come back to in a little while. But if we have a look here at printf, this is our function. This is like saying, here's a function called say, and I'm passing you the arguments hello world. Well, in C, here's a function called printf, which you might think should be just, well, why isn't it just print? But it actually means print formatted. But I'm just passing this function printf the same string, hello world. The \n just means once you've printed that, give me a new line. And again, we'll look into that a little bit more later. And we're going to break this down in today's presentation. But I do want to just keep doing this comparison and saying, you know, it may have seemed very intuitive to do it this way. This may not seem as intuitive, but it will become intuitive. We will get used to making sure that we put these semicolons at the end of our lines. So, functions, we've just had a look at, the say function. And again, really, we could have used other functions here as well. If you remember the blocky programming that we did, there were other functions where we could pass other parameters. So the printf function, as it is, can take any parameter in here. It doesn't just have to be hello world, and I'm assuming that some of you know that because I did see that some of you implemented that in your own programs as well. So we've got functions. We've also got loops. And when we're in the workshops, I saw a lot of you using the forever loop. And the forever loop just says, well, forever do whatever I put inside this block. So forever say the function, or implement the function hello world as the parameter. And that's what I can do here in C. So this is exactly the same. Okay, so I say while, which means whilst, just keep doing this, I guess, just while something is, in this case, true. And we can say, when we look back to week 0, we talked about, well, we could have used a 1 to represent true and a 0 to represent false. And here I'm saying, well, while true, while 1, and we can just assume that something is always true. So while true, do these things. Just like forever, do these things. While true, always going to be true. Printf, hello world. So if you'd use this block here in Scratch, this is how it would be implemented in C. Again, you'll notice we've got the curly brackets here, we've got the parentheses at the top, and again we've got this semicolon here. Again, things that may seem quite cryptic, but you will get used to using them. But sometimes we didn't want to repeat things forever. I remember looking at someone's code on Monday, and they wanted to repeat something only a certain amount of times. They didn't want to say, do this forever. So in Scratch, we would use a block like this. Now, the one that I'm about to present of how you would implement this in C looks even more cryptic than anything we've presented so far. But again, we can look past all of that and just realize that this is how we would implement a forever loop, a repeat until loop in C. We've got this for int I equals 0. Again, we've got a semicolon I less than 50. And all this will become very familiar to you, especially over these next 2 days. But again, notice, that's the block in Scratch. That's how it would be implemented in C. We then looked at variables. And variables in Scratch look like this. So we're saying set I, and remember we could call our variable whatever we want. But we said set this place in memory and call this place in memory I. In this example, we're going to put an integer in there, so that would be a good use of a variable name, I, to represent integer. And in that place in memory, I'm going to put an integer, the value 0. And you might have used these, for example, for some of you setting up lives or a score in Scratch. Well, how would that look in C? Actually quite nice. Quite nice. This is just saying here, again, look, this is my variable name I. Just notice I could have called that whatever I wanted. But in C, we need to tell the computer, we need to tell the place in memory what type of data I want to store in memory. So that's what this int does here. It's saying I'm going to store an integer in this place in memory called I. And what am I going to store in there? Well, I'm going to store the value 0. We also had Boolean expressions in Scratch. Remember these? I saw a lot of you using these on Monday. Yeah, the little green blocks. And this is saying, well, compare what is in I, and if we think about what was in I in the previous slide, well, I had 0 in it. Compare what is in I and see if it is less than 50. Well, that in C, very kindly, is exactly the same. Compare what is in I and see if it is less than 50. So that's how you would do Boolean expressions in C. And again, if you didn't want to just put an integer in there, you wanted to compare variables. So this is how you'd implement it in C, but be aware that in C, you would have had to actually assign values to those variables before you implement this. So somewhere in our program above this expression, we would have to say int x has this value in it, and int y has this value in it. And then we can conduct this comparison here. We also had conditions in our blocks in Scratch, which looked like this. And again, actually, although it looks, again, very cryptic in C, quite a lot of text on there, but it actually, if we relate it, and I've tried to put them side by side, it actually pretty much says the same thing, really. We've got the if x is less than y, then in Scratch. And we've just got here, if x is less than y, so the first bit is the same. we then got these curly brackets, and then we've got the say function over in Scratch, and we've got the printf function over in C, and then we've got the else command here in Scratch, else if, and we've implemented that with the else if x is greater than y in C. We've got the function again, we've then got the else command, and then we've got the function. So you can see there's a lot of familiarities with it. It's just that we've got to start typing these now rather than just dragging the blocks. And something you'll experience is you'll get some syntax errors. So like I said, you'll probably miss out the semicolon occasionally, and you will make mistakes. But embrace those mistakes. When you start experimenting with C, and you start getting the errors, embrace them, because you're about to learn something. You've done something wrong. The IDE, the software we're going to use to actually write our C code, will tell you when there are errors. And so if you can try and understand and interpret those errors, you know you're about to learn something because you're going to fix it. Although it's likely that you'll probably make the same mistake several times, the amount of times you miss semicolons off. We also had arrays. Now, this is slightly different in C, because in Scratch, we had something called a list, which is where you could store several pieces of data, one after the other. And how many of you implemented lists in your Scratch projects? I didn't think so, because I didn't see many on Monday. But there is a feature in Scratch that looks like this, where you could set up a variable, in a sense, but you could store multiple values in that variable, not just one. You could store many things. You could create, for example, a list whereby you're collecting objects in your game, and each object you collect gets put in a list. And then you can retrieve items from that list. And in Scratch it looked like this. It said, well, my list is going to be called argv, and I want to retrieve the first item from that list. Now in Scratch, if you do have a list of items, in Scratch, the first item is actually referenced as item 1. But in C, what you would do is the same again. This is my list, as it were, although we call them arrays, and they're slightly different, and we'll come on to that later in the course. This is my list, as it were, called argv, just like I'm referencing a list here in Scratch. But this is saying get the first item in that list. Because in C, we actually start, if you remember back to week 0, where we started talking about binary, and the smallest value you can have when we're talking about binary is 0. Computers count from 0 to 1 to 2 to 3 to 4. Just because of its ease of use for Scratch, getting that concept in your head is quite tricky. So they just started their list counts from 1, but in C you have to count from 0 upwards. But if you had a list in Scratch, that's how it would look, and that's how you'd implement it as an array inside C. So we're just going to have a little bit of a closer look at this program here. This is the most, well, it could be argued, but this is possibly the most simplest program you could have in C. All this does is prints hello world to the screen. But you'll notice that in order to do that, these are the basic building blocks that I need just to print the words hello world. And so if we have a look at this a bit closer, when you think about what you did in Scratch, when you grabbed that block that was when green flag clicked, that's just like doing this in C. Int main. Main is, if you just imagine, it's like the green flag. If you don't have it, you won't be able to run anything in C. Just like if you didn't have the when green flag clicked in Scratch, nothing would work. You have to have this because it's the main program, it's the main function that executes when you run your C programs. This printf we've already talked about. It's another function, just like the say function or the say block in Scratch. This will simply call that function and pass it the argument hello world. And this is source code. This is what you would write in an application that we're going to introduce to you shortly. A very simple program in C to print hello world. Now, to talk a little bit more about the source code, I'm going to ask Ocean to come forward and take you back a little bit in terms of what we were talking about in week 0 and how this builds on the ladder structure of the base, zeros and ones, all the way up to building applications. So Printf version.
Right, so now, if I can, so now we know how to transition from a blocky language like Scratch into a text-based language like C. And I know a lot of you have been really looking forward to this, and you're really excited to write your own text-based programs, and I promise you we will get there. In fact, if we do get time at the end of this lecture, Murtaza is going to actually do some live programming for us and show you guys how to write your own programs and run your own programs. But just before we get on to that, what I hope to do is give you a theoretical understanding of what actually happens when you run a program. And to be a little bit more specific, let me ask a question. And this is quite a long question, so I'm going to ask you guys to focus through this. So if we go back way back to the beginning of this course, of week 0, lecture 0, Mr. Wood said that fundamentally, computers are just electricity. We plug in power, and that electricity goes through the circuit through billions of these tiny things called transistors. And if it receives a high voltage, we say that's a 1. If it receives a low voltage, we say that's a 0. And that's why, at its very core, a computer only understands zeros and ones. It's only made up of zeros and ones. And just as we as humans, we communicate through and we understand words in the English language. And if we look at this piece of code, it's made up of words like we're including some file, there's some main function or some main program, and we're printing out some words. A computer can only understand zeros and ones. And it does not take a computer scientist to look at what's on the screen here and say that those are not zeros and ones. So my question is, how does a computer actually understand the program that we are writing? Remember, the computer doesn't speak English. The computer is not a human. It doesn't know what words are. So that's the question that I'm going to be tackling today. And the short answer to that question is that what's on the screen here actually gets translated into a literal series of zeros and ones. But that answer isn't very satisfying, so I'm going to walk you through it step by step. But just before we go on, some terminology. As Mr. Wood said, what's on the screen here is called, if I go back, the source code. And that's the code that we as the programmers, we as the humans write down. And as I said, we as the humans can understand this. Words are in there, English is in there. But to a computer, this means absolutely nothing at the moment. And just before I go on, I want to reintroduce this idea of a ladder. And we mentioned this in our very first week. And it's that in computing, there's a higher level and a lower level. And just to recap through it, at the bottom, we've got the actual circuitry and the electricity going through the transistors, the literal zeros and the ones that make up a computer. And just above it, we've got some hardware components. We actually ripped apart a computer and showed you guys the RAM, the CPU, the hard drive. And slightly above that, the operating system, which transitions the software into the hardware. And above that, as we've been messing around with, we have programming languages. And you guys have been messing around with Scratch, so you know that we can use these languages to create applications or games. And what's interesting about this ladder is that at the to an average user or an average user of technology or computers, all they care about what's at the very top here, the applications or the games that you create. So if you showed your Scratch project to one of your friends who aren't sitting here right now, they'd only care about moving around the arrows and playing your game. They don't actually care about the individual blocks you put in place, how you implemented the game. All they care about is playing the game. But we as computer scientists actually want to understand every step of this ladder. So today we're going to take our first step to doing that and actually zoom in to the bottom side of this ladder and try to understand how we get from a programming language, which you saw is quite high up, into the literal zeros and ones of a computer. And I'm actually going to get rid of this, but just conceptualize that there's a higher level and a lower level. So let's get on to tackling that question. We begin with the source code, which, as you can see, is quite high up. It's written in a programming language, in English, in words that we the humans can understand. And the first step to translating that is putting it through something called a compiler. And what the compiler does is it takes a piece of source code and outputs what's called assembly code. And we're actually going to see some examples. So if you can't really understand what it is at the moment, that's fine. But the difference here is that assembly code is a little bit lower down. So it's actually getting closer to the hardware. It actually has instructions for individual places in memory and registers in the RAM and in the processor. So whereas the source code only talks about words and just like print this word, the assembly code will actually say go to this space in memory and put this word in or something like that. So it gets a little bit closer to the hardware and begins mentioning the hardware of the computer. And now we put this assembly code, now even at this moment, actually I should say, the assembly code is still written using alphabetical letters. It's still not in zeros and ones. So there's one final step. We have to put it through something called an assembler. And what that does is it outputs machine code. And machine code, as you will see, is literally just a series of zeros and ones. And you may be asking, how do we actually translate what is in the source code into a series of zeros and ones? What does the compiler and the assembler actually do? Well, that's a very packed and complicated question, and to be honest, I don't know the full answer to that. But the simple way of answering that is that in every step of the way, the computer breaks down the initial code, the initial program, into a series of very, very small, very, very simple steps, simple instructions, if you will. And these very simple, kind of fundamental, basic instructions have been pre-programmed into the CPU by Intel when they make their processors. So Intel would have literally programmed into the CPU, if you see this series of zeros and ones, you're going to create some space in memory. If you see this series of zeros and ones, you're going to add two numbers together. So they have a certain set of pre-programmed instructions, which are very, very simple. And the way to get to those very simple instructions is by breaking down the initial program and just continuing to break it down until it gets very, very small. So we're actually going to see some examples. And actually, I should mention, this whole process of getting from source code into machine code is called compiling. And that is a little bit confusing because if you look very closely, the process of getting from source code to assembly code is also called compiling. So we actually have one word for two different things here. And they do mean two very different things. One from source code to assembly, one means getting from source code to machine code. So even though we have the same word, you can kind of tell from the context what you want it to mean. So now, let's actually get into some examples. You know this is source code. We've been through this a lot, and we don't have much time, so there's really not a lot to talk about here. But now, assembly code. This looks a little bit more exciting, and it looks kind of cryptic. It is written using English letters. You can kind of see some words there, file, section, string, something like maybe mov or move, if you will. And as I said, there's some instructions that are specific to a computer. So if we look here, we're moving, if you look over here, this move L, what this does is it moves whatever value is stored in this space in memory into this space in memory. So it's moving values. And there's instructions like calling the function printf, pop, and pushing certain values in memory, and those two words are going to become more familiar to you as this course goes on. So we can see here that it's actually mentioning certain registers within memory, or certain places in memory. And we can see we're going lower down that ladder. And now, before I show you guys the machine code, just keep in mind that we're breaking down the program step by step here. So, as Mr. Wood said, this is arguably the simplest program you can write in C. But just imagine how a computer would break this down. I'm just going to shut up. I'm just going to show you the machine code, actually. This is the machine code. This is the actual machine code for printing hello world. And the first thing you notice is, there are two things you'll notice. One, it's not actually zeros and ones, but I'll get onto that. But the second thing is, this is very, very long, and it seems very complicated for such a simple program. And that's why I'm saying the computer is actually breaking it down into a step of very, very simple instructions. That's why there's so many of them, which is why the code is so long. Secondly, this is not zeros and ones. You can see some letters in there. You can see 2s, 6s, 7s. The reason for that is this has actually been encoded into a system called hexadecimal. And we're not going to really get onto that today deeply, but just to briefly talk about it, it's just another number system. Just as binary is base 2, decimal is base 10, hexadecimal is base 16. You can go research that on your own. We're not really going to go into it, but basically, if we encode binary into hexadecimal, we basically shorten it. We shorten it by like 4 letters actually. So what you see on the screen, which is encoded in hexadecimal, if this was in binary, it would actually be 4 times as long. So just keep that in mind of just how long this machine code actually is, and how if you break down even the simplest of programs, you can end up with something as complicated and as long as this. So now let me wrap up with just by looking at this diagram once again of how we get to source code all the way down to machine code. First, we compile it using a compiler, then we assemble it using an assembler. And right now, you may be sitting there thinking, Ojan, that's really interesting, and I'm fascinated right now. But how does this actually matter? How is this relevant to me? And the answer is that it is actually very relevant, because when you start writing your own C programs, you're going to need to know how to compile a program and have a theoretical understanding of what it means to compile a program and how to run a program. And now hopefully you do have the theoretical kind of foundation of what's happening, but you don't actually know how to practically go about doing it. So now I'm going to get Murtaza on to actually show you guys practically how you can not only write your own programs, but how you can compile them yourselves and run it through the terminal.
Right, so we've talked a lot about the theory of compiling, but really we want to know how we actually do this compiling. How are you guys going to take that source code that we've been talking about, that whole printf hello world, and actually run it and make it work? So I'm going to show you exactly how we do that. This is the CS50 IDE. This is something you guys are going to all get very familiar with very soon. So you can see it's kind of dark right now. I can change that turn it off of night mode. So that you can kind of see a little bit better. This is basically a computer where we're going to be writing code and compiling it. And you guys can sign up. We'll give you instructions how to sign up from edX. We'll post them on the group. So there's three main sections of this here. Here you have a file tree where you'll see all your files that you'll write. In the middle, there'll be a text editor. And here you can open terminal windows. And I'm going to do that now. I'm going to create a new file called, I'm going to create it and save it straight away as hello.c. And I'm going to write this source code that we've been talking about for this entire time. Give me a second. So now I've written this source code. The next step, as we remember, is to compile it into machine code so that the computer can run it. And we do this through a terminal. Now, a terminal is something that can probably look scary at the beginning if you haven't really worked with it before. But it's a way for you to write commands to this computer and ask it to do stuff with your files. So if we run a command, clang hello.c. So clang here means C language, stands for C language. It's a compiler. Clang is the name of the compiler. And we're telling it that we want to compile the file hello.c so that we can run it. So let's do that. Oh, whoops. Right. First of all, we see that there's an error straight away. That's because I missed out my semicolon. So clang, being really nice, it tells me exactly where that error was and how to fix it. So I'll do that and try compiling again. Okay, it seemed like nothing happened. It didn't say anything. Well, usually when we're writing programs, nothing happening is actually good because that means that there's no errors. Like we saw what happened when there was an error. But now we need to know how to run this program. So there's a syntax in terminal for running a program, which is / followed by the name of the program. So a.out happens to be the default name that Clang has decided for the programs that it generates. If we run it, we see we get hello world. So we've actually managed to write our program and actually get it to execute. This is pretty cool. Now let's start thinking about what would happen if we actually remove this \n that we were talking about earlier. We don't really know what it does. What's going to happen if we remove it? Let's change the source code, compile it again, and run a.out. So now, when we ran it here, there was a new line given. That was because there was a \n. But now since we removed the \n, there's no new line. Well, that's not good. We don't want that because we don't want to be running commands on the same line that we ran our program. So let's put that \n back and hopefully fix that error. So save, run it again. What happened? Well, if we think about our steps, we updated the source code, but we didn't actually compile it again. We didn't compile it into a.out. We didn't save the source code as the machine code. We didn't turn it back into machine code. So the a.out is still the old machine code, whereas our updated source code is different. So what's running here is what the old source code was before we recompiled it. So let's compile it again and run it again. Now we've fixed our program again. It's outputting the new line again. Now, a.out. Why is it called a.out? We don't like this. Let's change the name of this file to something better. So what we can do is actually give Clang some parameters. So what we can say is call the output file hello. So -o just means the next thing I'm going to say is going to be the name of the output file. We run this. Now we have a new file, as you'll see it popped up there, called hello, and we can run /hello in the exact same way. So there pretty much is how you're going to be building and running all of your C programs for the next few weeks. And you'll get really used to using a terminal to do this. It can seem a bit cryptic at first, because you're not really used to giving your computer commands by typing them. Usually you click, double click, or drag. Like if you're running a program on your home computer, you'd probably double click the icon. But here we've got this / stuff going on. We can do other things with the terminal as well. So if I wanted to say delete this a.out because I don't want it anymore because I have hello now, well, I could go here and right click and do delete. That would be one way of doing it. That would work. The other thing I can do is literally type a command to do that. So if we do rm, which stands for remove, and remove hello, it's going to ask me to confirm. So I can just type Y for yes. And now we deleted hello. Now, I actually didn't want to delete hello, which is a mistake. And I can't get it back now. So that's a problem. So be careful when you're deleting files here. Because if I accidentally deleted my source code, it would be very difficult to get it back. So instead, we can just make hello again, because we haven't changed the source code, and remove a.out, which is what we wanted to do. Oops. Right, so rm space, and then the name of the file, Y to confirm, removes it. There's other commands that we can do. So we have a file tree here that shows us all the files here, but we can actually see those from the terminal as well, just by typing ls, or list. So here, it's showing us all the files that exist in the directory that we're in. And the directory that we're in is workspace. That's what this line over here shows you. Then the $sign just means write your commands after this. So our folder over there, workspace, has hello and hello.c. Hello here is highlighted in green and has an asterisk. That's just the CS50 IDE's way of telling you that hello is executable, or it's a program that you can run, as opposed to just a text file or some other kind of file that you can view and edit. You can actually run hello. That's why when we do /hello, stuff actually happens. And that is pretty much the main features of the CS50 IDE. So you've got your file tree, you've got your text editor, and you've got your terminal. And so one more thing, going back to Clang for a second, this command here, it's starting to get quite long now. Why don't we just simplify this? What if there's a way to not have to write this kind of command every single time? Well, there happens to be a, let's just get rid of our program and compile it again. There happens to be a command built into Linux, or Linux, however you want to pronounce it, built into Linux called make, which makes compiling easier for developers. So instead of having to type out long commands every time, clang hello.c -o hello, that's not very long, really, to be honest, but they can get quite long. If we just make hello instead, we can see that actually the command that is running is quite long. And when we get into more complicated programs, the commands that we're going to need to run are going to be quite long. So we wouldn't want to run that every time we want to make a program. So the make program knows that if I want to make a program called hello, the likely case is that its source code is called hello.c. So it pretty much guesses that for us. When I said make hello, it looks for hello.c and compiles it in the exact same way that we manually compiled it. And that works exactly the same. Whereas if I tried to make a program that doesn't exist, there's no rule to make target by. That means that it didn't find the source code for by, so it didn't know how to make it. So this make program is going to be something that we also see a lot. We can actually customize the way make works later on when we're building programs with multiple files that have to be linked together at some point. That's make allows us to keep those commands, write them only once, and not have to run them again and again and type them out manually. And that's pretty much the CS50 IDE. It's running in something called Cloud9, but you'll sign up through edX. You won't actually go to the Cloud9 website at all. That's basically it. Now, one more thing, we've been having these 3-part lectures so far. It's not always going to be the case like that. Sometimes we'll have 2, sometimes we'll just have 1 person delivering the whole lecture. But when it makes sense to divide it up to into 3 parts, that's when we've decided to divide it up into 3 parts. So it won't always be this kind of linear thing between the 3 of us. And I think that's pretty much it. Thank you.
Also, if I could add one thing, we're actually going to make a post on Facebook about how to actually get onto this and how to sign up, so don't worry about that for now. And now you can clap from the top.
Yeah, so as Ocean said, how to get onto this. I'll keep the video running actually. How to get onto this, how to set up an account we will post that. For the next, well, for quite a lot of the next problem sets that you're going to be given, you will be solving those problems in C. So you do need to become familiar with this interface. You need to become familiar with Cloud9, which is, again, is what Mataz has told you, is the IDE, is the place where we're going to work, is your terminal, is your file storage. It's all free, but don't go to Cloud9. I emailed Harvard, the Harvard CS50 team last night, and they're saying, look, go through our portal, go through our way of getting to it, and then you can all have free accounts. Because if you try and go Cloud9 tonight, you'll realize that actually there's paid accounts and non-paid accounts, and what do you get with each. Just wait for the Facebook post until you start actually signing up to this, okay? But please do become familiar with it. Once you have signed up, have a little play. Tomorrow's lecture is in here. It's going to be by Ocean and Mataza. I'm not going to be part of that one. Tomorrow's lecture is in here, and it's going to be a lot more about how to write these C programs and what we can do with it. The last thing, in fact, that is it. So that is CS50 DC Week 2. Thank you for coming.